So now I want to do a second example, but I want to do it for a problem where it would be better instead of using that head loss equation to use the standard energy equation. So here's a different example involving a turbine. We've got airflow and it's steadily going through a turbine. Here's the turbine. The inlet diameter is 12 centimeters. The inlet pressure is 10 atmospheres. The inlet temperature is 250 degrees Celsius. And the velocity at the inlet is, average velocity, constant velocity, 35 meters per second. At the outlet, we have same diameter, 12 centimeters of outlet. Pressure is dropped to 1 atmosphere. The temperature is dropped to only 5 degrees Celsius. And we also know that the turbine is putting out a significant amount of power. The turbine is putting out 500 kilowatts of power. So we're supposed to estimate, or asked to estimate, both the outlet velocity and Q dot. So we're going to estimate outlet velocity and Q dot. Let's see if we do that. Once again, of course, you could stop the video at this point and try it on your own and see how it goes. And if you turned it back on now, very good, we'll continue. So here we go. We're going to write down the first law equation, the energy control volume equation. So it's W dot minus Q dot equals M dot H in minus H out plus V squared in over 2 minus V squared out over 2 plus G times Z in minus Z out. So that's our conservation of energy equation for control volume. We know that air is an ideal gas, and that's going to affect us in two different places on this problem. The first place it's going to affect us is right here. We need to replace that with an ideal gas relationship. So we know that for ideal gas, the change in enthalpy is Cp dt. Cp can be approximated for air as about 1 kilojoule per kilogram Kelvin. If you look it up, it does depend on temperature, so you could probably pick a slightly more accurate value if you wanted to. I'm okay with 1 personally. In this particular case, we know that Z in is equal to Z out. That's very apparent from the picture. And also clearly, in fact, Z's for gases rarely matter because the heights have to be huge for them to add up to any real energy. So we're going to rewrite this. Q dot equals W dot plus M dot times Cp, T out minus T in. Notice the sign change because I've moved, Q is no longer negative. So I'm solving for Q now. So T out minus T in plus V squared out over 2 minus V squared in over 2. So that's what's left. This is looking pretty good. I have the two temperatures. I have the work. Do I have a mass flow? I do not yet have a mass flow, but I think I'll be able to calculate that. But I do need some velocities here. So I got these two velocities. I do have one of the velocities. V in was given to me as 35 meters per second, so that's easy. 35 meters per second. Now again, control volume analysis, we're assuming there's only one velocity. A funny thing to assume in a fluid mechanics class where we're actually supposed to be studying fluid flow. But in some cases, that's a valid approximation that there's only one velocity at the inlet. It's all 35 meters per second. We'll have to get into when that's really a good approximation later in the class. But we need V out. And so how are we going to get V out? And we're going to get V out from mass conservation. So to get V out, use M dot in equals M dot out. And we know the relationship for that in terms of density and area and velocity is that. So rho in V in A in, right? So those two things, that's for both M dots in terms of density, area, and velocity. So we're going to solve that for V out. So V out, therefore, is equal to V in times A in over A out and rho in over rho out. Well, A in over A out is just 1 because D in equals D out. So D in equals D out. Therefore, A in equals A out. So that term is not an issue. So we can simply say that V out is equal to Vn times the ratio of these two densities. So that's a good equation. Looks like it ought to be easy to solve. How will we find densities? Well, once again, it's an ideal gas, right? So I'm going to use the ideal gas relationship. So I need rho. So I'm going to use P equals rho RT. I know that R is equal to 287 joules per kilogram Kelvin. I know that T varies with the inlet, so I'm going to have to change. I'm going to have different P's and different T's. But I can solve for rho. So at the inlet, rho is equal to P in over RT in, which when I put everything together, I have 10 atmospheres, 10, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, newtons per meter squared divided by 287 joules per kilogram Kelvin divided and 523, which is the Kelvin equivalent of 250 degrees. So whatever I said it was, whatever the inlet temperature was. Let's see, inlet temperature, yeah, 250 degrees. So that's my formula, and I turn the crank with my crappy calculator, and I get 6.72 kilograms per meter cubed. And I believe that. Why? Because I know that at room temperature and pressure, the density for air is about 1 kilogram per meter cubed. So I believe that at 10 atmospheres and 523 degrees, it could be 6, almost 7 kilograms per meter cubed. It makes sense to me that it would be higher because of the really high pressure, but it's not going to be 10 times higher because the temperature is also higher. So that makes sense. If it were like 672, I wouldn't believe it. Or if it were 0.006, I wouldn't believe it. So I'd like to check these things, make sure they make some sense to me. Then the outlet density is going to be P at the outlet divided by R and T at the outlet. So I plug those numbers in, 10100 newtons per meter squared, that's 1 atmosphere, and 287 joules per kilogram Kelvin. Again, that's my R value, and then 278 Kelvin. And that comes out to 1.27 kilograms per meter cubed, and I definitely believe that, because this is at 1 atmosphere and just it's kind of cold, so it's not going to be like 1 kilogram per meter cube, but it's pretty close because it's regular, just almost like room air, a little bit cold room air. So those are believable to me. So finally, I get my outlet velocity is 35 meters per second. That is my inlet velocity times this ratio, 6.72 over 1.27. And that equals 185 meters per second. So it's moving really fast. It's screaming out of there. And you could say, well, does that make sense? And it does make sense because it came in at 10 atmospheres and it's being vented at 1 atmosphere. So that's a huge pressure change. So that gas is being driven by a very, very large pressure change, leading to a very, very high outlet velocity. All right, so now we got to plug all that back into my Q equation. So that's what I was asked to find. So I found my outlet velocity, but I was also asked to find the heat loss. So Q dot equals W dot, 500,000 joules per second, plus M dot times my CP, 1 kilojoule per kilogram Kelvin, times 278 minus 523. Those are my inlet and outlet temperatures. Obviously, outlet minus inlet temperatures. And then I have my outlet velocity squared over 2 and my inlet velocity squared over 2. So that's my Q. This isn't going to work as written, right? Because I have kilojoules here and I have joules here. So I have to be careful with that. This is going to come out as joules because these are meters per second squared. So I got to be in joules land here. So I got to stick in joule land. So I got to convert that to joules, which hopefully I will easily be able to do. So but I also need M dot, right? So I don't have my M dot, so I got to get that. So M dot is easy to find because I know everything I need for this. Rho in, A in, and velocity in is M dot, and that just comes out to be 6.72, the density I just found, kilograms per meter cubed, times the area, which is 0.12 over 2 squared, times pi, that's pi r squared, times V in, which is 35 meters per second. Turn the crank, and you get M dot equals 2.66 kilograms per second. So I plug 2.66 kilograms per second into this equation to get 500 kilojoules per second plus 2.66 kilograms per second times negative 245 kilojoules per kilogram plus 16,500 joules per kilogram. Of course, I'm going to multiply the 2.66 kilograms per second through. I get Q dot equals 500 kilojoules per second minus 652 kilojoules per second and plus 43.9 kilojoules per second. Add all those up and I get Q dot is equal to negative 108 kilojoules per second, or negative 108 kilowatts. So this system is dumping heat out as it progresses.